Okay, so what I'm going to be doing is a voltage transfer curve for this particular circuit here. This is a TTL 74LS04 type of circuit. That's just simply an inverter that you can do this also on an oscilloscope as well in real life. Okay, so in the simulator, I'm going to simulate that and let's see what we get. This is what we get. We get this type of response. So when Vn is all the way up to 2.5 volts, it's going to be high. Then when it goes beyond 2.5 volts, then it's going to be low. So that's definitely the characteristic that you would expect from a inverter. However, I'm going to point out one fact here, that this is an ideal characteristic. I mean, you have, let's take a look at this using some cursors. You have exactly, on cursor 1, 5 volts exactly, and then you have, on cursor 1, exactly 0 volts, for V out low. So V out high, is exactly 5 volts. V out low is exactly 0 volts. That's a ideal characteristic, and it's not the least bit practical. That's not exactly what happens in real life. That's why it's a good idea to do this on the oscilloscope in real life, because when you take a look at a data sheet, according to the data sheet, you have your 74LS04. When you calculate noise margin, you're considering the V in low and the V out low. So V in low, again, maximum it can tolerate is 0.8 volts. V out low, the maximum that it's going to give you is 0.4 volts. So you're looking at a 0.4 volt difference here between V in low and V out low, which means that you have a 0.4 volt noise margin. Then for the V in high, anything that is at a minimum, from 2.0 volts and up is considered high. Now under these conditions, V out high will be at least 2.7. So what does that do? That gives you a 0.7 volt noise margin there. So that is just how that works there. And this is the data sheet for it. And so the data sheet is about what happens in real life. So don't expect, this type of response in real life where you have V out high 5 volts, V out low 0 volts, V in low for it to be 2.5 and less, and V in high to be 2.5 or more. Don't even expect that in real life. Simulator definitely is still a very, very good tool. It's very useful, but you just have to know the limitations of it. Let's go ahead and take a look at this circuit in real life and do a voltage transfer characteristic or a voltage transfer curve for this particular gate. Okay, I am going to do a very short demonstration here for a TTL inverter, and that TTL inverter is 74LS04. I'm going to trace a curve, so basically I'm going to be doing a DC sweep with it and get the voltage transfer characteristic out of it. So if I reduce my voltage, we'll see at some point this will go high. Okay, so around there. It may exhibit some hysteresis, but maybe not. So this is in a YT format, and I'm just doing this just to see, what happens and what can I expect. Okay, so what I'm going to do next is I'm going to start sweeping across a range from 0 to 5 volts. And so that's what you have. Okay, so 2 volts per division, and I have 2.5, so 2 times 2 is 4. Half of 2 is a 1, and that gives you 5 when you add them all up. Okay, so that makes sense. Next thing is I'm going to go to display, and I have the choice to go from YT format over to XY format. We want to retain the data on the screen so that we can look at it, so we're going to go to persist and turn that to infinite so that it'll display it and keep it up there for us. And so that is what it is. So you're now seeing the voltage transfer characteristic of this inverter gate. The only other thing that I might want to do is change the channel 1 divisions, and I'm only going up to 5 volts, so I'll be able to see the whole thing. Okay, so what I just wanted to take a look at here and make a comparison is between what I obtained here on the oscilloscope as well as what is on the data sheet. How does that correlate? How does, like, is it consistent? And just do a quick comparison. So according to the data sheet, Vn high, well, Vn high is when the inverter goes low. Because we're studying an inverter, that can be kind of confusing, so you have to make sure that you understand and interpret this correctly. So Vn high, again, is when the inverter goes low. And the minimum, according to the data sheet, is 2.0 volts. So at least at 2.0 volts of a minimum, Vn high is going to activate. So that basically means that around, according to our oscilloscope graph here, we have 1 volt per division on our oscilloscope graph. We're at like maybe about 1.4, and they're saying a minimum of 2.0, so we're actually a little bit under that according to the oscilloscope reading. Next is Vn low. So when Vn is low, then the inverter is high, and they're telling us, according to the data sheet, 0.8 is the maximum value, and that looks very consistent according to what we have on the oscilloscope, because again we have 1 volt per division, and it looks like about 80% of 1 division. So the Vn low, again, that's when the inverter outputs a high, and when Vn is low and we're looking at the edge of the corner there, that's at about 0.8 volts, so that's very consistent. And the next thing to take a look at is V out high. V out high is just simply the high output of the inverter, and according to the data sheet, it's a minimum of 2.7 volts. We have 2 volts per division on this, so 2 and then 4, so we're a little bit over 4, maybe about 4.2, 4.4, something like that. And according to the data sheet, it says the minimum is 2.7, so we're above that. And then last, there's V out low, and V out low should be approximately, according to different types of testing conditions, it should be approximately 0.4 or 0.5 volts. V out low on the oscilloscope looks to be approximately about 0.2 volts. So it's a little bit under that, maybe about that much, but it seems to be a little bit under that, and that is just what it is. So overall, everything was very, very accurate, and the only thing that was a little off was V in high, but that's okay because actually it made our noise margin even larger than we would expect, because V in high versus V out high, the difference between 2.7 and 2.0 is 0.7 volts, but actually our V in high is closer to maybe like 1.2 or 1.4 volts. So 2.7 minus 1.4 is larger than 2.7 minus 2.0. So actually we got a little bit better of a characteristic than we would expect concerning V in high. Okay, so let's go ahead and get back into the oscilloscope analysis. So that's it. That's your TTL inverter gate. And so as you can see, once it gets to approximately 1 volt, then action of the gate happens, and then that's that. So you can calculate your noise margins from that. And this is a good way of seeing this on the bench instead of only just doing everything through the simulator all the time. So that's it. That covers all that I wanted to do in this video, this short video, as a demonstration on how you can use your oscilloscope to plot voltage transfer characteristics. And that is it. Hopefully it was helpful for you. Thank you for watching, and have a nice day.